Hello, and welcome to another episode of Wired for Precision, the podcast where we explore the brains and backbone of modern industry, instrumentation, automation, and everything in between. I'm your host, Phil. Today's topic is at the very core of measurement accuracy, reliability, and operational safety: calibration. If you've ever handled a pressure gauge, a temperature transmitter, or a digital multimeter, you've probably heard the word, but what does it really mean to calibrate a device? In simple terms, calibration is the process of comparing a measuring instrument to a known reference, usually a standard with a known accuracy, and adjusting it if necessary to align its output. In industry, calibration is not just a best practice, it's a requirement, especially in sectors like pharmaceuticals, oil and gas, food manufacturing, and aerospace, where even the smallest deviation can lead to compliance violations, downtime, or worse, safety risks. Let's clear up some confusion. Verification checks if the instrument's readings fall within an acceptable tolerance. Calibration is the comparison against a known standard. Adjustment is the act of tweaking the instrument to correct any deviation found. You can verify without adjusting. You can calibrate and still choose not to adjust, depending on whether the error is within limits. Every calibration needs a reference. These are often traceable to national or international standards, like NIST for US, BIPM for global, or the ISO/IEC 17025 standard for calibration laboratories. Traceability ensures consistency. It means that your instrument's accuracy can be linked back, through an unbroken chain of comparisons, to an internationally recognized standard. For industries under ISO 9001:2015 or regulated environments like GMP, traceability is non-negotiable. Let's talk about the actual tools and methods technicians use during calibration. The right tool not only ensures accurate calibration, but also improves efficiency, safety, and documentation integrity. Some of the most widely used tools in the industry include multifunction calibrators. These devices can simulate and measure voltage, current, especially 4 to 20 milliamps, RTDs, thermocouples, frequency, and more. Great for technicians who handle a variety of field instruments. Documenting process calibrators. These go a step further by recording calibration data on the spot and generating reports or certificates. They help ensure compliance with ISO, FDA, and GMP documentation requirements. Dry block calibrators. Used to calibrate temperature sensors, these devices heat up, or cool down, a metal block to a precise temperature, allowing you to insert sensors for calibration. Liquid baths. For even more precise temperature calibration, liquid baths offer uniform heat distribution, ideal for calibrating multiple sensors at once or when accuracy is critical. Pressure calibrators or deadweight testers. These are used to apply precise known pressure to test and adjust pressure sensors, transmitters, and gauges. Deadweight testers are especially useful because they're based on fundamental physics: mass, gravity, and area. Loop calibrators. These are designed specifically for current loops, often used in analog process signals, 4 to 20 milliamps. They can simulate, source, and measure loop current, making them indispensable for control loops. Each method depends on what you're calibrating. For example, if you're working on a flow meter, you might use a reference meter or a prover. For a load cell, you'll need certified test weights. It's about matching the right tool to the device and the environment you're in. And don't forget the software. Many teams now use asset management and calibration software to schedule, track, and document calibrations. It's especially useful for large facilities managing hundreds or thousands of instruments. Performing calibration in the field requires more than just technical skills. It calls for discipline, accuracy, and a strict adherence to standards. Here are key best practices you should follow during field calibration. 1. Establish a baseline, as found reading. Always begin by recording the instrument's readings before any adjustments. This as-found data is critical for traceability and analysis. 2. Follow a multi-point check. Don't just calibrate at one value, test at multiple points across the range, typically 0%, 25%, 50%, 75%, 100%. This helps identify linearity or hysteresis issues. 3. Zero and span adjustments. When necessary, adjust both the zero or offset and the span or gain to bring the device within spec. Some transmitters allow digital trimming using HART communicators or field calibrators. 4. Labeling and documentation. After calibration, the instrument should be labeled with the calibration date, due date, who performed it, and whether it passed or failed. Good documentation includes instrument tag number, reference standard used, environmental conditions, results, as found or as left, tolerances. 5. Respect the environment. Avoid calibrating instruments in unstable or extreme conditions unless necessary. Vibrations, temperature swings, or moisture can introduce errors. 6. Ensure safety. For hazardous locations, use intrinsically safe or ATEX certified equipment. Always follow lockout tagout procedures and PPE protocols. A well-calibrated system is not only accurate, it's also auditable and safe. And if you ever get audited, your documentation and procedures speak louder than words. This is one of the most debated questions in any quality or maintenance meeting. How often should we calibrate our instruments? The truth is, there's no universal answer. But here are the key factors that determine calibration frequency. First, instrument criticality. Instruments used in safety critical or regulatory compliant processes must be calibrated more frequently. For example, sensors involved in batch processing for pharmaceuticals may require monthly or even weekly checks. 2. Stability of the instrument. Some instruments, especially digital and newer models, have high stability and low drift over time. Others, like analog pressure gauges, can drift more quickly, requiring more frequent recalibration. 3. Manufacturer recommendations. Most equipment suppliers provide suggested calibration intervals. Always start with their guidelines and then adapt based on performance over time. Fourth, historical performance. If your instrument has a history of staying within tolerance, you may consider extending the interval. This is called interval optimization. On the other hand, frequent drift means you may need to shorten the schedule. 5. Environmental conditions. Instruments exposed to harsh environments, vibration, humidity, corrosive gases, should be checked more often. 6. Usage frequency. A flow meter in continuous 24/7 operation will wear faster than one used once a week. Many organizations adopt a risk-based calibration strategy using a combination of failure mode analysis, process impact assessment, and real-world drift trends. Some also use automated calibration management systems to analyze trends and adjust intervals dynamically. Calibrating in the lab is one thing, doing it out in the field is another. Here are some of the real-world challenges that technicians and engineers face during field calibration. 1. Accessibility issues. Instruments are often installed in hard-to-reach or hazardous locations, at height, in tight spaces, or within live systems that can't be shut down easily. Second, limited downtime windows. Production rarely stops just for calibration. Engineers are often under time pressure, especially in plants running 24/7. That means calibrating quickly, efficiently, and without causing delays. 3. Dealing with uncooperative instruments. Some devices may be outdated, lack modern communication protocols like HART or Foundation Field Bus, or show signs of failure. Knowing when to calibrate, adjust, or recommend replacement is part of the job. 4. Environmental extremes. Outdoor calibrations can mean dealing with intense heat, cold, or rain, all of which affect both the technician and the instrument. portable, ruggedized tools become essential. 5. Human error and inconsistent practices. Without standardized procedures or proper training, calibration data can vary widely. This is why SOPs and competency-based training are so important. 6. Inadequate tools or reference standards. In some remote locations or smaller facilities, technicians may not have access to high-precision reference standards, leading to poor calibration reliability. 7. Documentation gaps. Failure to properly document calibration steps, results, or certification data can lead to non-compliance during audits, even if the calibration was performed correctly. In short, calibration is as much about planning and precision as it is about adaptability and problem solving. It's where the theory meets the ground, literally. Calibration is more than just a technical task. It's an art, a science, and a commitment to precision. It's one of the ways we ensure safety, efficiency, and trust in every reading we take. Thanks for tuning in to this episode of Wired for Precision. If you learned something new today, I'd love to hear your thoughts. Drop a comment below. Don't forget to like, share, and subscribe for more content. Until next time, stay sharp, stay measured, and stay wired for precision.